Welcome back. Let's continue. Our final talk today is by John Pardon from Princeton University. So just a few words of introduction. As I believe many people here, I was first familiar with John's work when I saw his paper on distortion of knots, in which he answered a famous question of Gromov, showing that there exist knots with arbitrary large distortion, actually torus knots. Well, it's a remarkable work which he did when he was a student at Princeton University. He then went to do a PhD at Stanford under supervision of Yakov Ilyashberg. Let me mention that it's a second invited talks of today's afternoon delivered by Ilyashberg's former students. Okay, well, the first one was not here, but he was invited to give a talk. Well, John received Morgan's Prize for his work on distortion of knots, and since then he received many other awards, most notable Alan Waterman Award in 2017. And today he's going to talk about smoothing finite group actions on three manifolds. Please welcome.
Thank you very much. I want to thank the organizing committee for the invitation to give this talk. It's an honor and a pleasure to be here. So I'll be talking about smoothing finite group actions on three manifolds. So to begin, I'll talk about what is a tame group action. So we know what a smooth group action is. It's when every group element acts via diffeomorphism. Now there's an intrinsic notion, which is just topological. A group action is called tame if it's smooth with respect to some smooth structure. Okay, so I could take a smooth group action, conjugate it by some arbitrary homeomorphism, it's still tame. And an action is called wild if it's not tame. Now it's sort of silly to talk about tame and wild if your manifold itself doesn't have any smooth structures at all. So we'll assume M has at least one smooth structure when talking about this definition. Okay, so here's a basic example of a wild action. Well, it's not really one example, but a class of examples. So suppose you have a topological manifold which is not smoothable, has no smooth structure, but it has a finite G cover which does have a smooth structure. Well, then the G action on the cover M tilde is wild, because if it were smooth with respect to any smooth structure, that smooth structure would descend to the quotient M, and M would be smoothable. Okay, so one can produce examples of this, examples of non-smooth manifolds with covers which are smoothable using surgery theory. So this is valid in high dimensions. These examples exist. And this gives a wild action which is even free. And in low dimensions, meaning at most dimension 2, everything is tame. So there are examples of wild actions in dimension 3. So I want to give this example. So I don't have a picture of the Alexander Horn sphere, I'm sorry, but I take the Alexander Horn sphere. So what is this? You take an ordinary sphere, you sort of push up 2 fingers. Each of those fingers then splits into 2. They sort of do a clasp. They don't quite come together. Then each of these pairs, this pair and this pair, each of those 4 fingers again sprouts 2 more, and they do a clasp, and they have this infinite procedure. Okay, that's the Alexander Horn sphere. Take the exterior. Okay, the interior is just homeomorphic to B3. The exterior is not. The exterior minus the sphere itself has infinitely generated fundamental group. So the exterior is some wild space. And Bing considers the double of this wild space. So just take 2 copies, glue it along its common boundary, and you get something which you think might be some strange space. It turns out it's just the 3 sphere. So that's Bing's result. Okay, so you get a space X, the double of X has this obvious involution, and so you get an involution of S3. And it's a wild involution, because its fixed set is this S2, the common boundary, and that's wildly embedded. Right, the complement has infinitely generated fundamental group. And a smooth involution would have smooth fixed set, so a tame involution would have tamely embedded fixed set. Okay, so in particular, this is a wild action. Okay, so I want to say at least a small about this construction of Bing. So we consider the Bing doubling operation. So, well, it's now called the Bing doubling operation. That's not what Bing called it. So inside a solid torus, we can consider this this link, the middle one on the picture. So that's a link inside a solid torus, and given any knot, it has a solid torus neighborhood, and I can just take the image of this link under the embedding of that solid torus. So in particular, okay, if I start with an unknot and do this operation, I get the second link. Now this link has two components. I Bing double each of them, and I get the third picture here, and you just can keep going. So I've drawn the links, but they have these solid tori neighborhoods as well, and these are nested. So you can consider the infinite intersection of these. Let's call that n. And as it turns out, this is homeomorphic to C cross the interval, where C is the Cantor set. So how do we see this homeomorphism? Well, okay, let's start with the horizontal plane that just cuts each of these guys in half. Now the horizontal plane clearly intersects n in a Cantor set. So to show that n is homeomorphic to a Cantor set cross an interval, I'll give you a one-parameter family of surfaces, all of which intersect n in the Cantor set, and which partition n. So what do? I start with the horizontal surface. That's one of my surfaces. Then I start. Move 2 fingers up these sides. One up here, one up here. Those, as I move up, these keep intersecting n in the Cantor set. Once I get to this part, it's sort of problematic. So each of these fingers I've pushed up now splits into 2, one going around sort of this finger on this side splits into 2, one going around this side, one going around this side. This one also splits into 2, one going up here, one going up here. And you see I'm constructing the Alexander-Horton sphere this way. So this not only shows that n is homeomorphic to C cross the interval, it also shows you can describe the space, the double of the exterior of the Horn sphere, by taking this 3 sphere and taking this n and collapsing the fibers of the projection to the Cantor set. Great. So far, this is nothing's really happened. We've just given an alternative description of this doubling of the exterior of the Alexander-Horn sphere in terms of the Bing doubling operation. Now, the key result that Bing proved, which implies this isomorphism, is the one I've stated here. This is not at all obvious statement. So if you Bing double enough, the statement is that if you Bing double enough, then each of these components, well, there's an isotopy which sends each of the components to have arbitrarily small diameter. Obviously, this is taking place inside the solid torus. I mean, if you just have this in S3, well, you can just shrink it all down. That's not what I'm doing. Okay. Right. So this is the corollary. Right. So this this shrinking procedure actually also gives you a way of thinking about this involution. So these Bing doubles have a symmetry, namely reflection across the horizontal plane. I can look at this isotopy, this mysterious isotopy produced by Bing, which applied to some high Bing double takes everything to to have small diameter. And conjugate this reflection by that isotopy. And now I get some involution, which fixes some very complicated two-sphere. And as you shrink the components more and more, this converges to this exotic involution. So in particular, the horizontal plane, as you take its image under these shrinking isotopies, as m goes to infinity, it converges to a wildly embedded sphere. Okay, so in particular, this being involution is a uniform limit of smooth involutions. Okay, so there are other examples of wild group actions on three manifolds, sort of like wild knots. You can construct many examples. Sometimes the fixed set is a wild knot instead of a wild surface. That'll be important later. Okay, so here's the theorem I want to talk about. It's simple to state. Every finite group action, continuous finite group action on a three-manifold is a uniform limit of smooth group actions. Okay, what about the parenthetical? There are some mathematicians who can be sure they've proved a result before they actually write down the proof. I'm not one of them, though, and I haven't written down the proof of the theorem. But I'll explain the proof in the talk, and you can decide what you think. Okay, so a couple of remarks. Okay, this statement certainly was asked as a question some time ago. Obviously, it's only of interest for wild group actions. Uniformly close does not imply topologically conjugate. I mean, this is invariant under topological conjugacy, so it would be pretty bad if this theorem would have no chance. It would be obviously false if uniformly close implied topologically conjugate. This theorem doesn't say anything new about existing examples of wild group actions. All the constructions of wild group actions on three manifolds from the previous slide are defined as uniform limits of smooth actions. So really, this theorem is simply saying that those are all of them. That construction gives you all of them. Okay, so even this sort of trivial corollary of the theorem is, as far as I know, not known. Okay, so for the rest of the talk, I'll talk about the proof. Okay, so we begin with Smith theory. So Smith theory, in the most basic case, talks about order P automorphisms of spaces and in particular manifolds. Okay, what Smith theory actually says is that if you have an order P automorphism of a manifold, then its fixed set is a Z mod P homology manifold. Okay, and in this low dimension that we're considering, dimension of M is 3, then you can actually upgrade that to say the fixed set is actually a manifold. Okay, no one's, I mean, there could be different components of different dimensions, though. The dimension is not at all determined by the order of G. Okay, and moreover, it'll be important to understand when this fixed set can be a surface. So that only happens when the prime is 2, and I might call this a quasi-reflection. So your involution exchanges the two sides of the surface and reverses orientation. So this gives us at least a basic course understanding of what finite group actions do on three manifolds, at least for cyclic groups with prime order. Okay, as you might guess, there's a version of Smith theory for arbitrary finite group actions, even for actions of Lie groups. But this is all we're going to need. Okay, so if we have a three-manifold with a group action, we smooth it over successively larger and larger loci in M. So first there's a locus where the action is free. Next, I want to look at the locus where the action is either free or it's of this Bing type, what I just call the quasi-reflection. So the stabilizer is Z mod 2, and the fixed set of that involution is locally a surface near the point. So this is also an open set. Okay, so first we're going to smooth the action over the locus where the action is free. This is sort of trivial. I mean, the only way you can have a wild action which is free is when you have manifolds which aren't smoothable. And in dimension 3, everything is smoothable by Bing and Weiss. So smoothing over M free is essentially a trivial application of their theory. Smoothing over the reflection locus. So this was essentially proven by Craggs. So he stated it, I think, just for involutions of S3 fixing and S2. But as far as I can tell, the argument applies in general. And the key is a result of Bing, which I'll state. And okay, and then we smooth over the complement. So in this work on the Hilbert-Smith conjecture in dimension 3, there is a lattice of incompressible surfaces, which played an important role. And so I'll also use that in this proof. Okay, so let's talk about a little bit more carefully about the how we smooth the action where it's free. Okay, so right, let's just suppose the entire action is free. It's essentially the same. Okay, so the action is free. The quotient is a manifold, just a topological manifold. Bing and Weiss say it has a smooth structure. So let's call that M mod G S. Okay, so we can pull the smooth structure back to M. Now, of course, it may be completely different from the smooth structure on M that we started with. So this, the identity map from M to MS is not smooth. Probably not smooth. But what Bing and Weiss proved is that any homeomorphism of three manifolds can be uniformly approximated by a diffeomorphism. So we can approximate this identity map by a diffeomorphism. And now we just pull back the action under phi. So we have G acting on MS, that's smooth. We pull it back under our diffeomorphism. That's just essentially conjugating it by phi. Now that's smooth. And it's close to G because phi is close to the identity. Great. Now what about this? What about smoothing over the reflection locus? Right, so the key result is this result of Bing. So what does Bing say? So it takes any surface properly embedded in a three-manifold. Let's say it's a wildly embedded surface. So any possibly wildly embedded surface has a tame re-embedding which is close to the identity. So this theorem is actually a very similar character to the theorem that we're in the process of proving. So every wild embedding is a uniform limit of tame embeddings. Right, so for example, the Alexander Horn sphere is defined as a uniform limit of tame embeddings. And this theorem is basically saying that's the only thing you can do. Take a uniform limit of tame embeddings to get a wild embedding. Okay, so not only does every wild surface have a tame re-embedding, the tame re-embedding is unique up to isotopy. Okay, so if I really wanted to say this precisely, what I would say is that for every epsilon greater than 0, there's a delta such that every tame re-embedding which is delta close, given any two tame re-embeddings which are delta close to the original embedding, there's an epsilon small isotopy between them. Right. Okay, so how do we apply this? So we have our original fixed set of our involution. That's a surface. Probably it's wildly embedded. We have a tame re-embedding. That's the red line here. Now, this tame re-embedding certainly is not fixed by the involution. There's no reason it would be. The tame re-embedding gets sent under sigma to some other surface. But this other surface is also a tame re-embedding of our wild surface. So the second part of Bing's result says there's an isotopy. There's an isotopy from I to sigma composed with I. And moreover, it's supported near in a small neighborhood of this surface. Okay, so using this, we can just define our new involution. So what do we do? So the fixed set is going to be the tame re-embedding of our original fixed set. So what I do first, I apply sigma. Okay, so there are two sides, call them U and V. First, I apply sigma. So that sends U. Okay, clearly I've mislabeled this. It should be sigma of U on the bottom and sigma of V on the top. Okay, we send U to sigma of U on the bottom, and then we apply the isotopy. So that sends this red curve, sigma of I of M sigma, back to I of M sigma here. Okay, so this gives us a homeomorphism from U to V, and moreover, it's the identity on the boundary. Okay, so I want things to be involution, so on V, I just decide to do the inverse of that. Okay, so now we have, and away from this set, this just agrees with the original involution. Okay, now the fixed set is the tame re-embedding as a tame fixed set. Okay, now you can complain that I didn't actually smooth the action. I just made the fixed set tame. But that's really enough, because now we can apply the previous argument that we used to smooth things over the free locus. Right now, you can take a quotient by the group action, and now we get a reasonable space. Now we get a manifold with boundary. And Bing and Moise applies just as well to manifolds with boundary. That's a smooth structure. You do the same argument. Okay, now you probably noticed that we didn't actually need step one. We should actually just really go directly to step two, and then apply this argument. To step two didn't care about the action being smooth over the free locus. But for sake of exposition, I explain step one first. Okay, so and this is Craig's argument. Okay, so now we want to smooth over the rest. So X will be this, the rest of M. So first we need to know what this set is. So this is not hard. Okay, suppose you have some point in M which is not in the reflection locus. So what does that mean? That means either the stabilizer has order strictly greater than 2, or the stabilizer has exactly order 2, and the fixed set of that involution locally is not a surface. Okay, so in that case, you're good. By definition, you're in this set. Right, so let me just say again in words what X is. So we take all the elements of prime order in G, we look at their fixed sets, and we only take the components of dimension 0 and 1. Now, of course, the only other components you could have are components of dimension 2. I'm assuming the action is generically free. The only other components you could have are components of dimension 2, and those only occur for involutions. So this is almost the same as taking all of MG, but not quite. Okay, so back to the proof. what do we do when the stabilizer has order greater than 2? Well, let's look at the subgroup which preserves orientation. So that has index at most 2 and is therefore non-trivial. So it has some element of some prime order, which preserves orientation. And that's all we need, because we just have to show that this element of prime order is not order 2 and reflecting near x and reflecting with reverse orientation. Okay, so there's no need to understand all the details of this argument. This is just some case analysis. The corollary that we care about is that this locus, this bad locus that we still need to smooth the group action over, has covering dimension at most 1. It's essentially, it's essentially one-dimensional. Okay, so what is covering dimension 1? Just means they're arbitrarily fine covers with no triple overlaps. That's the definition of covering dimension 1. Okay, so let's take a neighborhood of this bad locus x. So x is some of horrible one-dimensional locus inside M. But our group action is smooth away from x. So I can take an invariant neighborhood. The invariant neighborhood is very nice, has smooth boundary. And I take a cover of this neighborhood by open sets, small open sets with no triple overlaps. This no triple overlaps is going to be very important. Right, so here's a picture. I have 7 open sets up here. They have, I guess, the 4 yellow-orange ones and 3 green-blue ones, and you see there are no triple overlaps in this cover. Okay, now our goal is going to be to find properly embedded incompressible surfaces in these double intersections, which are invariant up to isotopy. Okay, now why do we want to do this? Well, we're going to cut up our locus A by these surfaces, and since they're G invariant, I'm going to get the action of G is going to descend to an action on the PCs. Okay, I should point out this invariant open cover. Right, this is a G invariant open cover, and G is allowed to permute the pieces, permute the open sets UI. Okay, so this is just a picture of what these G invariant open incompressible surfaces might look like. I mean, you might imagine here that G is sort of Z mod 3 rotation of the 3 legs of the tree. And then you'd want to know that this surface is sent under a generator to this surface. This surface is sent under a generator to this surface, all up to isotopy, not on the nose. Right. Okay, so how are we going to find invariant incompressible surfaces? So in each of these double overlaps. So these double overlaps, they're three-manifolds with 2 ends. So if I have a sequence of points inside a double overlap UI cross UI intersect UJ, if I have a sequence of points in that intersection, and that sequence of points sort of escapes the intersection. Well, it can either converge to something in UI or it can converge to something in UJ. It can't converge to anything in UK for any other K, because that would imply that UI, UJ, and UK have non-empty intersection. And there are only double overlaps here. So if you're in UI, this three-manifold UI intersect UJ, it has just 2 ends. You can either go off towards in the UI direction or go off in the UJ direction. Okay, so we're looking at compact, properly embedded incompressible surfaces. So incompressible, well, there's a geometric definition of incompressible, but under some orientability assumptions, it's the same as saying that the map on fundamental groups is injective. So you can think about it that way. So the map from F into UI intersect UJ is injective on pi 1. Okay, and the same on the boundary. Okay, and I want to consider surfaces which separate the two ends. Okay, so now that you have a picture of that in your head, I'll give you the picture. So A has boundary, right? That's this. These dark lines. UI and UJ are parts of an open cover of A. So this is a three-manifold with boundary. So our surfaces have boundary, have circle boundaries along the boundary of A. They might also have some genus, and I want to consider only surfaces which separate the two ends. So here are two such surfaces. I've drawn them disjoint. Of course, you might have elements of S of UI cap UJ which can't be isotoped to be disjoint. Okay, so we can introduce a partial order on this set of incompressible surfaces. They're comparable if they can be isotoped to be disjoint, and you pick which. You have to pick a favorite open set. Either you like UI more or you like UJ more, and I guess you say the surface which is closer to the one you like more is bigger than the other one. Okay, so you can check that this is a partial order. Great. So now the real non-trivial fact about this collection of incompressible surfaces is that it's a lattice. So every non-empty finite subset has a least upper bound. And this is the key property that we need. And the proof uses minimal surfaces. So when I was thinking about the Hilbert-Smith conjecture, I was realized this statement would be really nice if it were true, and thought probably it's not true, but fortunately Ian Egel told me that it was, and said this is how it could be proven. So what's the point? Every incompressible surface has an area minimizing representative. You don't need mean curvature flow to do this. This is much more some older existence theory for minimal surfaces gives this to you. And there's this work of Freeman, Hass, and Scott, which this gives you a very general set of results, which basically say that if you have two incompressible surfaces, and you take their area minimizing representatives, then those area minimizing representatives minimize the number of intersections that take place. So in particular, if you have two incompressible surfaces which can be isotoped to be disjoint, then their area minimizing representatives are disjoint. So what this means is that if you take the elements of S are isotopy classes, you can take representatives of those isotopy classes. So pick area minimizing representatives, and those representatives simultaneously realize all of the order relations. There's no reason this should be true. Other than the fact that it's proven. There's no reason from the previous slide. If you only know this material on the previous slide, there's no reason you would expect such representatives to exist. And the lattice property follows essentially immediately from having these representatives. Okay, so this is why we want the lattice property. We get this immediate corollary that we have the incompressible surfaces that we want. So how do we do this? Well, okay, take arbitrary surfaces, the arbitrary elements. Now they have they might not be G invariant, but we can just take their orbit. So that's some finite collection of elements of S of ui cap uj for every I in J. Of course, remember that the group G could permute the pairs I comma J, but that's fine. We just take a collection of Fij for every ij, take the orbit under G, and take the least upper bound. That's G invariant. Okay, so this is basically all we need. So we have our area minimizing representatives like this. Not area minimizing. We have our G invariant incompressible surfaces. So what do? So remember, this is our neighborhood is A. A is the sort of neighborhood of this trivalent vertex that I've drawn. So we have our surfaces, and we can cut A along the surfaces. And we get pieces AI corresponding to this, the elements of the open cover that we started with. And G acts on these pieces, possibly permuting them, or probably permuting them. Okay, I say it acts up to homotopy. Now there are actually many different things I could mean by that. I could mean that, every element of G gives me a diffeomorphism, and composition, they compose up to isotopy. I could say, phi of G times phi of H is isotopic to phi of GH. I could go a little bit farther, and I could say that I choose isotopies between phi of G, phi of H, and phi of GH. And I require that those isotopies are compatible in the following sense. So I could look at phi of A, phi of B, phi of C. That's isotopic to phi of A, phi of BC via chosen isotopy. And then that is isotopic via chosen isotopy to phi of ABC. I could have gone the other way around the square. I could have gone from phi of A, phi of B, phi of C to phi of AB, phi of C, and then gone to phi of ABC via chosen isotopies. So I get a circle of isotopies of diffeomorphisms, and I could require that to have be contractible. And you can actually keep going. You can specify disks filling in each of these squares, and then you can form a cube for every 4 elements in your group and require that extend to a ball of diffeomorphisms. So the action we start with is very nice. The action, it's an honest, it's phi of G, phi of H simply equals phi of GH. But now the surfaces are not invariant under G. So we only get this action up to homotopy. But I said there are a few different ways, a few different things I could mean by up to homotopy. So similarly, there are a few different things I could mean by the surfaces being G invariant up to homotopy. You can say exactly the same thing about cubes. You can say it for surfaces being invariant under the group action. Now we're lucky though that Hatcher proved that the space of Hatcher proved that every isotopy class of incompressible surfaces is contractible. So being invariant up to homotopy actually gives us invariant up to however many homotopies we want to up this tower. And so that means that this action here up to homotopy means it's as strong as you want in the sense that I just described. Okay, so that seems to be important. I believe it's important for the next step. Although maybe one could get away with less. It's certainly sufficient for the next step. Right, so we have a homotopy action of G on this three-manifold, the disjoint union of all these pieces, and we'd like to upgrade it to an honest action. So to do this, well, we'd like to use the geometrization decomposition of these pieces. Now, fortunately, these pieces are sort of small three-manifolds with boundary. I don't think we need to appeal to Perelman to geometrize these. Thurston proved it for Haken manifolds, and these have boundaries, so these are just fine. They could have non-trivial JSJ decomposition with some Seifert-Farbert pieces. So maybe just say what's the proof if they're hyperbolic. So if you have a piece which is hyperbolic, it has some hyperbolic structure. Now the hyperbolic structures, we know from Mostow rigidity, the hyperbolic structures on the closed three-manifold, there's only, if it exists, there's only one. On an open three-manifold, a three-manifold with boundary, well, in fact, Mostow rigidity applies if the boundary is a bunch of tori also. But if the boundary has some pieces of higher genus, then there are many hyperbolic structures. And in fact, each hyperbolic structure gives you a conformal structure on the components of the boundary of higher genus. But that's the only variation in possible hyperbolic structures. So what do? We have a group action on our hyperbolic three-manifold with boundary. Now, Kirchhoff tells us, Kirchhoff and later also proved by Gabay, tells us that there's some conformal structure on the boundary which is invariant under our group G. It's a Nielsen realization problem for surfaces. So we can choose a conformal structure on the boundary which is fixed, and therefore this rigidity result of Martin says that the action of the group G actually fixes the hyperbolic structure on the whole three-manifold. Okay, so in fact, not only does G act by isometries, not only does G act by diffeomorphisms on the pieces, it acts by isometries on the hyperbolic piece. Okay, in general, there could be Seifert-Farbert components of these pieces. Then one has to work a little bit harder. There's a paper, or maybe multiple papers of Bruno Zimmermann, which addressed the Nielsen realization problem for Seifert-Farbert spaces. And as far as I can tell, the upshot is that if you have just an action of G up to homotopy in the weakest sense, so just a map from G to the mapping class group of your three-manifold, your Seifert-Farbert three-manifold, that's not enough. But you just need one more level. So you need these chosen isotopies between phi of G, phi of H, and phi of GH, for which these squares are contractible. And then, that's not the way he phrased it, but it's equivalent, or at least sufficient. So that solves the Nielsen realization problem for those Seifert-Farbert pieces as well. Okay, so that's basically the proof. We have now an action of G by diffeomorphisms on each of these pieces. You glue them back in to get an action of G by diffeomorphisms on M. Now, why is this action C0 close to the original action? Well, I can just take a very fine cover. Right, that was we showed that X, this bad set, and X mod G have covering dimension 1. We can make this cover as fine as we want to. Of course, the elements of G might do something crazy to each of these pieces, but the action on sort of pi 0 of the pieces is the same as the original action. And that's all we need to ensure that things are C0 close. Okay, so I think I'll stop here. Thank you.
Thank you, John. Questions?
what about higher dimensions? Is this true or false?
It's,
Or what do you
already
expect?
difficult enough.
True. So, okay, one could ask whether, so I gave this example at the very beginning of non-smoothable, or of wild free actions. Now, if C0 close implied topologically conjugate for free group actions, then the answer would be negative. But I don't know if that's true. It certainly seems unlikely. And maybe there's, I mean, I don't know the answer. Is the real thing to say.
More questions? May I ask something? So this one-dimensional invariant or fixed point, it's a graph, right? It's a three-valent graph, or it's topologically a circle. I mean, in smooth category, it will be a circle, but in your case,
I'm not sure what the fixed set looks like. I mean, okay, if your action is like Z mod P, I mean, if your group is Z mod P, then it's
the group is Z mod P, but the action is continuous.
Sorry?
The action is continuous.
Yeah, then it's a wild knot. Yeah, that's what Smith theory says. If it's Z mod P, then the fixed set is a wild knot. If it's a more general group, then I'm not so sure.
I'm about Z mod P, but, so it's a knot. It can be wild knot, but it's a knot.
Yes.
Right?
Yeah. I mean this is what
important
Smith theory tells you.
Okay.
Yeah. In dimension 3. In higher dimensions, you can have fixed sets which are not manifolds. You take, what do you do? There's an involution of the 4 sphere whose fixed set is the Poincare.
Because for smooth action, it's actually a circle, right?
Sorry?
For smooth action in Smith,
the fixed set is always smooth.
Yeah, okay. Well, let's thank John and all the speakers of today again, and if we have more questions, we can discuss later.